Okay, hello to everyone. I'm very happy to see you all here. Today we are also very happy to have Beatrix, who is going to tell us about the semiclassical gravitational path integral and random matrices. Beatrix, take it away.
Thanks, Felipe. Thanks so much for having me. I would have loved to visit, but I think when I emailed Felipe, can I visit? I was like, yeah, Vancouver is in Canada, so it's like an hour. I was like, it's going to be close. But yeah, clearly I'm in European distances over here. So anyhow, I hope you're all doing well with the flooding and everything. So good. Okay, so indeed, so what I'm going to talk about today is mostly like this paper, which is basically the same title as my talk, the semiclassical gravitational path integral and random matrices, which came out just 2 weeks ago, which is in collaboration with an amazing collaborator, Gibbons. But let me just say that, basically this paper is just a tip of basically these 4 papers that we put out in the last 2 years of just trying to understand the gravitational path integral and random matrices and just to build this connection. So it's mostly based on this work, but you will see some of the results also coming from these papers. Very good. So I put this first slide over here before even putting a table of contents or anything. So because I figured maybe not, basically because I wanted to give you the bigger picture, why are we doing this? What are we trying to understand? What's the bigger picture? So okay, so let me just say that I'm not an experimentalist, but still I don't know, we kind of have these observations of the CMB. We have the explosions of the distant stars. We kind of know that we're entering this regime of accelerated expansion. So that in the infinite future, we're going to live in a de Sitter universe. Because basically we are assuming that this accelerated expansion is driven by a small yet positive cosmological constant. So, and this cosmological constant is really small, so it's a order 10 to the power of minus 120 in Planck scale. So it's a very small positive cosmological constant. And that basically, in particular, what this implies, you see my full screen, right? So in particular, what this implies is that, see you this little astronaut or so in universe. There's basically there's a bubble that's surrounding you, because and so this thing over here is basically the cosmological horizon. So because space-time is expanding, there's going to be at some stage not even light can reach you anymore, and that's basically what marks this cosmological horizon. So even if we're assuming that basically our universe exists beyond that cosmological horizon, that's how far as we can get. That's our little bubble, our observatory, basically. And just to give you some length scales, if we assume that the cosmological constant is this 10 to the power of minus 120, this cosmological horizon is at a distance of 20 billion light years. Good. Now, we have this bubble, this cosmological horizon, with basically the entropy area over 4G roughly. So inspired by the black hole horizon, we give this entropy the area over 4G law. And so basically, more technically, let me also give a number to this. So if you really calculate this area over 4G in a 4D spacetime, so then this is a order 10 to the power of 120. So we have this huge de Sitter entropy, which is really, really huge. This is orders of magnitudes higher than a black hole entropy. So this is a huge entropy. And more seriously, this de Sitter entropy, there's this notion of the Gibbons and Hawking proposal. And Gibbons and Hawking were proposing that you can calculate this de Sitter entropy from a Euclidean path integral. So basically what they were saying is that this basically the de Sitter entropy, or the exponential of the de Sitter entropy is encoded in this path integral over here. So SE is just the Euclidean action, the Euclidean Einstein-Hilbert action. Lambda is a positive cosmological constant. And M over here is basically a sum over compact manifolds. And most importantly, this Euclidean action over here, it has a dominant sphere saddle. Why is this sphere important? So the de Sitter space, the geometry of Euclidean de Sitter space is the sphere. So if you Wick rotate both a static patch or a global patch of the sitter, if you Wick rotate either of these in the Euclidean signature, you get this sphere. That's really important. That's not what happens in like ADS or so. If you Wick rotate a static or a global patch, you're ending up with a different geometry. In the sitter, if you Wick rotate the global patch or the static patch, you're ending up with this sphere. Good. So, and the punchline is one of the major open questions, of course, that we have at the moment is that we observe this huge de Sitter entropy. But the microscopic origin of this de Sitter entropy is not known. And actually, maybe I should also say this here. Like this formula is not so much of a new thing. Like this is really like basically the de Sitter version of the black hole thermodynamics. So you just said, I mean, usually you have like the logarithm of Z is equal to the entropy minus E over T, right? I mean, this is just the thermodynamics law. It's just that in the Sitter space, there's basically there's no energy, because the Cauchy slices in the Sitter spacetime, they're compact. So basically, there's no boundary. So there's nothing that you can associate to the entropy to the boundary. So that's basically just this term drops, and that's where. So this is not something incredibly new, and like you should not see this as like, oh my gosh, yeah, this is falling from heaven now. No, this is basically something that we've seen. Very good. And so basically, the goal, the very, very ambitious goal, or like is that we are trying to understand this setup over here in a two-dimensional universe, and where we can explicitly make sense of this path integral here. So we can really understand this path integral, because as it turns out, exactly this Euclidean path integral has been studied a lot in the past for completely different reasons, but which I'll explain like later on. But so this Euclidean path integral in 2 dimensions has been studied. We can explore it. It's known. So we can basically, our goal is to understand or to explore this S de Sitter over here, this object over here, semiclassically in a 2D universe. And as it turns out, in 2 dimensions, there's furthermore a microscopic model known like there's a conjecture completion basically of this path integral over here, which would give you a microscopic picture, and this microscopic picture is nothing else than a random matrix integral. So I figured that maybe, even if I'm taking ahead like the rest of my talk, but my attention span in a Zoom talk is still like the first 5 minutes. So I kind of hope that if you're dropping out at some point later, this is basically the punchline of what we're trying to do, and everything else that follows from now is like giving me to like this bigger picture here. Very good. Okay, so but now let me still like get to my outline. So I love penguins, but also like the spheres, really just like, okay, it's because the spheres is a very important object here. As I was saying, so my talk is really just like, I'm going to explain to you what's the gravitational path integral. I'm giving you I'm explaining what the semiclassical limit is. I'll highlight a bit more like the 2-sphere partition function, because it's a beautiful object. We will also discuss the higher genera. So basically, because as we will see, we will also capture higher genus contributions to the path integral and to the matrix integral, which basically the last part of my talk is going to be about multicritical matrix integrals, which are these random matrix integrals that are the conjecture completion of the gravitational path integral. I put this in parentheses over here. So maybe if time allows, I have some backup slides on time like Liouville theory. You will see just in 1 or 2 slides why I put it here. Very good. So let's talk about the gravitational path integral in 2 dimensions. So indeed, like in 2 dimensions, the gravitational path integral is basically just nothing else than this sum over topologies. So chi-h over here is the Euler characteristic. So chi-h is 2 minus 2h. So basically you have the sphere, which has Euler characteristic 2, and then the torus, which is like 0, and then you go down. And like indeed, like lambda is the the cosmological constant, and this bar theta over here is basically the coupling to of the Euler characteristic. Very good. So, and then you have like at each genus H, you have this path integral over here. So basically you have the metric and your sum, and you have this. it's weighted by like this interval over sigma h. Let me just point out also that if lambda is positive over here, then large area fluctuations are suppressed. So this is actually like really a setup in which it's good if you have a positive lambda. So this is basically our cosmological constant in 2 dimensions. And indeed, like, so basically it's a sum over this compact manifolds. So like, let me just also like highlight this. So we're really on compact manifolds. So we're studying the path integral on compact manifolds. Just taking this already ahead, like just because, I mean, this of course has also popped up recently, like this whole context of like matrix integrals and has popped up in the literature on JT gravity, but there's always like manifolds with boundaries. We're manifesting and manifolds on compact manifolds. Very good. So now the problem of the gravitational path integral in 2 dimensions is that there's generally no saddle. So the metric in 2 dimensions is like a highly fluctuating object. So you cannot really collapse this down to a saddle. So that's basically the problem of 2D. So in higher dimensions, this is fine, but in 2 dimensions, this is the tricky thing. You don't have a saddle. But and this is just, yeah, as I'm saying here, like the metric is highly fluctuating. But indeed, there are 2 possibilities to tame these fluctuations and to suppress. To tame the fluctuations for now. And there's 2 possibilities. Is that basically the central charge of this matter theory that you're coupling to gravity over here, you can send it to -infinity or you can send it to +infinity. So it turns out that if in the first case, case A, which is the case that I'm going to talk in the next, 20 slides or so, that's in this case, we find a saddle, like we find a sphere saddle, only if you also fix the metric of the physical, like the area of, we fix the area of the physical metric. So basically, imagine you have the path integral on a genus 0 surface, and then you fix the area, and then you send the matter central charge to -infinity, and in that limit, you're gonna find like a not fluctuating, like a really honest to God sphere. So basically, let me just say this, like, so here, what we are doing is that we are summing over all topologies, but we have a topology. So you're free to say like, okay, we are on a genus 0 surface, we have a sphere topology, but unless you have a saddle, you're never gonna end up with a geometry, and you need the geometry to still really start working. So this is really like the limit, the symmetric going to -infinity, and the fixed area, that's really the limit in which you have an honest to God sphere geometry. And this has been like discussed in a really beautiful work by Cosmological 40 years ago already, actually. So, and yeah, well, the other possibility to tame your fluctuations is that you send the matter central charge to +infinity. And this setup is then what goes under the name of time-like-Liouville theory. But time-like-Liouville theory comes with its own subtleties. So I think it's a remarkable thing. And let me just point out, so this is basically like these 2 possibilities, like sending symmetra to -infinity or symmetra to +infinity. These are really the only 2 possibilities that in 2 dimensions you get a sphere saddle. I mean, I think there was also this recent paper by this group in Stanford, where they've been discussing like JT gravity when you just like switch the sign. But there they found the sphere partition function being infinite. So there's basically no notion of like a sphere partition function in JT gravity. So if you're in 2 dimensions, if you want to have a sphere saddle, then take your Poisson, pick like case A and fix the area, or decide to go to time-like-Liouville theory. Very good. And I will also I will discuss this point into like more detail just in a couple of slides. So like this will get its own slide.
Beatrix, can I ask a question?
Sure.
So the fact that there exists a saddle, or I mean, you're stressing very much the fact that it is important to analyze whether a saddle exists or not. I understand that it is very convenient and in some sense important when it comes to actually computing this path integral. Mm-hmm. But if we forget about that for a moment, one of the things we've learned at least from the JT gravity perspective, is that there are contributions to the path integrals that are not saddles in the sense that they do not satisfy the equations of motion, but they are crucial. They're important when it comes to computing the path integral. So at the conceptual level, is there a problem not having a saddle?
I mean, the thing is, like you see, I mean, what we are really trying to do is that we are trying to test Gibbons and Hawking. And Gibbons and Hawking comes with the condition that you need to have a sphere settle. So it's just like, it's not what we're looking for anymore, right? So that was the Gibbons and Hawking proposal told you, look, you get a de Sitter entropy if you have a dominant sphere settle. So to some extent, we want to test, basically that's the goal. We want to test the Gibbons and Hawking proposal. But Gibbons and Hawking, they tell us you need to have a sphere settle. You need to have this is the settle that you need to have. So if you don't have a sphere settle, we can just not connect to Gibbons and Hawking.
I see. So if you want to make contact to the sitter, you want to have a sphere settle. Okay, I understand now. Thank you.
So the sphere settle you really need because we want to make contact with the sitter. And let me also, just because you're mentioning this again, so if we have like basically a large theta over here, so if this coupling to the Euler characteristic is very, very big, then this subleading contribution, so these higher topologies, they're also suppressed because they come with a negative KH. So if theta is very big, then you have like really this dominant sphere settle because everything else is going to be suppressed exponentially. Very good. Okay. So, okay, now I'm trying to basically explain you like this thing over here. So this object is really like this, it's like this path integral on these compact Riemann surfaces. Okay, so it turns out that in 2 dimensions, like, I mean, in 2 dimensions, the metric has basically 3 degrees of freedom. So, and you can basically then go to Val gauge, because you fix like 2 of them with the diffeomorphism. So you have like the thing that you have left is that you can go to Val gauge. So you basically can express your metric, your physical metric. So this is G. So when I'm saying, for example, that I have the topology, that means that I have like G, that I fix G. So on a sphere, on a genus 0 surface, for example, I can say, oh, I can take G being the Fubini's 2D metric or whatever kind of metric that you want on the sphere. But then this is a topology, you fix a topology. So unless you find basically a value of this Weil factor here that gives you that G is basically proportional to G tilde, you're not going to have the geometry. So you need to have a saddle or a real valued saddle of phi star or a saddle of phi star of phi that gives you also the geometry that tells you that this basically also this G tilde to some extent is going to be like a sphere, a round 2 sphere. Very good. So, and it turns out that if you go to Val gauge in 2 dimensions, that the gravity sector can be expressed in terms of what is known as the Liouville theory. So basically that's arising from the Jacobian. So of this change of variables, like basically going to Val gauge. And so basically this is this first term over here where I put the subscript L because it's the Liouville action. And then we still have this matter sector over here, and we have the ghosts, and the ghosts arise because we go to Val gauge. So these are just the standard BC ghosts that arise when you go to Val gauge. And let me just stress that here, this matter CFT that we added. So this is a matter CFT that we added by hand, basically. So we just decided to also add a matter CFT because this is going to be crucial in the end, like when we are going to try to relate this setup over here to a matrix integral. Very good. And this matter CFT is one of those minimum models that are like these 2m minus 1 minimum models. And let me just stress that, I mean, these are non-unitary minimum models, but they're non-unitary on a rigid space. So if you couple on this non-unitary minimum model to gravity, the non-unitarity might be more subtle than if you're in a rigid space. So this is also something that you have to keep in mind, that we're coupling a minimum model to gravity. Very good. So now let me get into like the details of like each of these individual pieces over here on an arbitrary genus H Riemann surface. So the sigma H over here is basically one of those things. Very good. So as I said before, we are going to Val gauge, and in Val gauge, basically the path integral is rated by this Liouville action over here, where this phi, it's just a Weil factor, it's the Liouville mode, like call it, I guess you're kind of familiar with it. So, and then the Liouville action on a general genus H Riemann surface is just given by the following Lagrangian over here. So where R tilde is just, it's the Ricci scalar of the metric G tilde. lambda is still our cosmological constant, which we assume to be positive. And yeah, exactly. And like this parameter Q over here is related to this parameter B in the following way. So this is really chosen in such a way that this Liouville theory is a CFT. And given that Liouville theory is a CFT, it has a central charge, and this central charge is related to this parameter Q in the following way. Now, in our original setup, we had a matter theory, we had a Liouville theory, and we had the ghosts. So if you don't want to have a conformal anomaly, we want to have that the central charges, the total central charge vanishes. So basically the matter plus the Liouville plus the ghost, which is the -26, is equal to 0. Now, if you're taking this thing and plugging it in here, you're going to find that Q is the subject, is basically related to the matter central charge in the following way, and B is related to the little m, like this m here in the following way. And asymptotically, so basically if you send m to infinity, you're going to then easily understand that the Liouville central charge gives us 6m. And this is what I call the semiclassical limit, so which is the limit in which I get this dominant piece in the action, basically. So this is the limit in which the matter central charge goes to -infinity. And remember, these were non-unitary minimal models. So the central charge of this non-unitary minimal models, this was negative from the get-go. So that's why I can take this limit to -infinity. It is equivalent to the b going to 0 limit, which you can, I think, easily see if you start like using this identity over here. So then it's equal to the b going to 0 limit as well. And it's from here, it is very straightforward. If you send c matter to -infinity, you're going to send q to infinity. And I haven't added this equivalence here, so but it's also equivalent to sending m to infinity. So I hope this is not an overkill. I'm just trying to stress like there's just like all of this are basically the semiclassical limit, just because I know myself. So the next 40 minutes most probably I will call the semiclassical limit once the b going to 0 limit and once the m going to infinity limit. It's all the same, like they're all related using like this formulas over here. Very good. Are there any questions on like Liouville theory? Okay, very good. Okay, so let me go to the genus 0. So that's the most tricky part, actually. So genus 0 is very tricky, unfortunately. So on genus 0, as I was saying before, this thing over here, because the Ricci is positive, and on it, like it changes. Like the Ricci is positive on genus 0, it becomes negative. Sorry, it becomes 0 on genus 1, and then it's negative on higher genus Riemann surfaces. But essentially, because the Ricci is positive on a genus 0 surface, you're not going to find a saddle here unless you fix the area. So that's basically this inside of Cosmological, and Seiberg later on has also discussed this in his notes. So basically on genus 0, you also need to fix the area of this metric over here. So this object over here, this g tilde e to the power of 2b phi, this was just my metric over here. This was just my physical metric. So I basically fixed the area of my physical metric over here. So basically I say that I have a sphere and it has fixed area 4 pi upsilon. So this upsilon over here is basically like times 4 pi is the area of this sphere. And okay, so and it's like the path integral is related by the Liouville action, and like this volume of PSL to C, like PSL to C is basically just the residual symmetry group that's left, even if you go to Weyl gauge. So this is an object that we've been studying, like in one of the previous papers, and it turns out that you can, I mean, once you fix the area, you can just like you have a dominant sphere saddle, which is good because you want to have the sphere saddle, because you want to relate it to the Sitter space. And then you can start studying all the fluctuations on top of the sphere saddle. So you have the sphere, and then you start like all loop orders, you can study the fluctuations on top of this sphere. And yeah, so it behaves in the following way. Now, just like for those of you, if you're an expert, like you know that the sphere partition function in general should go as upsilon to the power of c matter over 6. So that's the standard scaling of the sphere partition function. Of course, like here, this is not the case because when we put the area constraint, this is not a CFT anymore. So that's why here we're breaking that actually. Very good. But yeah, as I was saying, you can then study like the fluctuations on top of this round two sphere saddle. And then basically in the end, we don't want to have the fixed area picture though. So we want to have an unfixed area, or like just a normal thing, like basically the thing without this fixed area part here. So it turns out, like, I mean, you can very easily go back. You just do an inverse Laplace transform of this fixed area picture over here. And then you get the standard Liouville sphere partition function. And here again, like here really, like it goes as upsilon to the power of c Liouville over 6. So this is really like what we're expecting, because it's a sphere partition function. So the conformal anomaly dictates that it should go as upsilon to the power of c over 6. And let me just stress that this is the large, so this is a semi-classical sphere partition function. So here we're also already taking c matter to minus infinity, m to plus infinity, or like b to 0, like one of those limits, however you want to call it. This is a semi-classical sphere partition function. And very good. Okay, so basically, like me also just like, I know that this is very technical altogether, but what's really like the thing that we are trying to understand is like we're trying to understand the m scaling, or like basically the m scaling of each of these contributions here. So basically, we are trying to find a semi-classical approximation of each of these three ingredients over here, because that's the limit in which we have this round sphere saddle, which we can connect to the zero space.
But Beatrix, can I ask something here?
Sure.
So yeah, you explained that for fixed area, there is a saddle that is essentially an S2. So how do we understand this saddle in the fixed lambda computation? Is this some kind of saddle again? Because you did this Laplace transform, right? But there is no saddle there.
Oh, sorry.
So physically,
no,
what
but I mean,
first?
But I mean, here I'm really just taking like my result, like that I get from the fixed area point of view, and then Laplace transforming it back. I mean, I don't think that there's, and I don't think that there's a real interpretation of it when you like go back to like when you do this Laplace transform back. That's actually really subtle. So that's really the point. I kind of like time like Liouville theory. Just a time like Liouville theory, as I said before, it comes with its own poison, and in particular, there is no microscopic dual for time like Liouville theory, none. But yes, this fixed area constraint is an incredibly subtle and tricky and a bit annoying property actually. So I have some like just in the Outlook, I also comment on it because. And I don't want to take anything ahead, but like, for example, what does it mean in Lorentzian signature to fix an area? So we'll come to this like at some point later, but yeah, this fixing the area, that's the tricky thing here, or like but we have to live with it if you want to have a CS saddle in 2 dimensions. Very good. So the things like change if you go to higher genus. So if you go to genus which is bigger or equal to 2, then your Ricci scalar is negative, and I think this is just a uniformization theorem that tells you that you can kind of fix it to this constant. So and then basically, so you have this Ricci scalar on a Riemann surface. So these were my sigma h's, my little drawings here. So my Riemann surfaces, and they have basically area 4 pi upsilon. So this really just follows, but if you use the Gauss-Bonnet theorem for this Ricci scalar. And then it actually turns out, so there you're saved. So it would have been better if this would have also been the case for genus 0, but it's not. So if you're really like going to like this higher genus, then you find the saddle, you find this real valued saddle 5 star over here. And then you can basically just evaluate the Liouville action on this 5 star. And semi-classically, so this is last expression is really the expression that you get in the semi-classical limit, this b going to 0 limit or m going to infinity limit, takes this form. And then if you just basically plug this back into the path vertical to leading order, you're gonna find this object over here. And let me just stress that basically the leading contribution is this object over here. So this basically lambda to the power of minus h is again like the genus. H minus 1, m plus a half. So this first object over here is independent of the moduli. So the first object where the moduli are popping up is here, this functional determinant. Very good. I think this is interesting. Maybe it was obvious, but I think this is very interesting. Okay. Good. So basically, what did we have? So what did we win so far? We have the Liouville action on an arbitrary genus H Riemann surface. We have it on a genus 0 surface, and then we studied it with like fixing the area such that we got a sphere saddle, and we've been studying like the Liouville path integral on genus H bigger equal to 2. I'm just stripping off H is equal to 1 because there you have like the trace, and so like I'm going to be a bit sloppy with like H is equal to 1. Good. So now let me switch a bit, or like not really switching. I'm just going to the next ingredient of my gravitational path integral. And the next ingredient of my gravitational path integral was the CFT partition function. So I mean, let me just write this down again, like just not to cause. So this is Liouville, set matter, and set cost. So this was basically the object that I was interested in. So this should be an H. So, and this was just the fundamental domain. So what we've done so far is that we basically understood this Liouville part over here. So now we want to understand this matter part over here. And let me just maybe also like stress this because it took me some time to really understand this. So remember that I don't want to go back, but I mean, in the beginning, we had basically this thing over here. This was basically our path integral, and then there was a Z matter over here, right? So what this basically said is that we are coupling a matter CFT to gravity, but then we're setting all the couplings between not the non-identity operator and gravity to 0. So the only coupling, so the only operator that we're really turning on is identity operator. So that's why we are allowed to consider Liouville separately from the minimal model separately to the ghost, basically. There's no deep interaction between the two of them because it's the identity operator of the minimal model that we are turning on. Very good. Okay, so, but I don't know, these 2 2m-1 minimal models, they actually have made a prominent appearance recently. And so these are just these non-unitary minimal models. And as I was saying before, they're non-unitary in a rigid space. So things might change if you couple it to gravity, and things do actually change if you couple it to gravity. Because where is the non-unitarity in the minimal model? Okay, they have negative central charge, but the non-unitarity in these minimal models is encoded in the norm of the descendants. So the primaries of this minimal model, they're going to have positive norm. The descendants are the objects that are going to have the negative norm. That's what basically encodes your non-unitarity in some big blob. But if you couple a minimal model to gravity, I mean, you gauge in the diffeomorphisms. So you might as well also, like, there's also like the Virasoro group that's kind of included there. So you might as well have gotten rid of all the descendants. So I just wanted to stress this, that even if we have a non-unitary minimal model from the get-go, and we've learned like, okay, don't use non-unitary minimal models. But if you couple them to gravity, that might as well be much more subtle. So like we might as well get away with it. Okay, good. But these are non-unitary minimal models, and they have a central charge. And because they're like, I mean, they're not like these PQ minimal models. They just have a central charge. That's, I think, of the form 1 minus 6 p minus q squared over p times q. I don't know if you're not familiar with these minimal models. I mean, these are just like 2-dimensional CFTs, like the Ising model is a prominent example of the Potts model. These are just like minimal models. And like in this specific class of non-unitary minimal models, 2 to m minus 1, I think the most prominent example is the Yang-Lee model, which is I think the ferromagnetic phase of the Ising model. Someone correct me if this was wrong, but I thought that this is the case. So, and yeah, okay, good. So this M2 to M minus 1 minimal models, they have M minus 1 Virasoro primaries. So all minimal models have a finite number of primaries. And this specific class has M minus 1 primaries. And importantly, like, let me just stress this again, like, so they have like M minus 1 Virasoro primaries. So there's identity operator, and then there are M minus 2 other primaries. And because these are non-unitary minimum models, there's the identity operator over here, 1, and this is going to have, like, of course, it has conformal dimension 0, but then everything else that comes about as well has negative conformal dimensions. So really, this is really different than unitary minimum models or unitary CFTs, where you have the identity operator, and then everything else builds on top of the identity operator with, like, positive conformal dimension. For this non-unitary minimum model, you have this identity operator with vanishing conformal dimensions, and then everything else comes basically has less, like, lower conformal dimensions, so it goes down. And that's what I was saying. So the most prominent example, at least for me, I mean, there also, I think if you're more of a statistical physics and statistical physicist, then you're more familiar with the other models as well. For me, the Yang-Lee model is maybe the most promising one. It's this model that has central charge minus 22/5. And it has indeed, like, 2 Virasoro primaries, like 3 minus 1, so 2. And there's the identity operator, and then there's this O12 operator, which is conformal dimension minus a 5th. And let me also just stress, because it's going to be important later on, you have the fusion formula for this 2D CFTs, for these minimum models. And for this fusion formula, what I'm going to need is that I have, like, the identity operator. So I'm really specifying a Yang-Lee model for now. So the Yang-Lee model has indeed, like, this O11 and the O12 operator. But then hidden, there's also this O13 and the O14 operator. It's just that you identify the O13 with the O12, and you identify O14 with O11. So basically, this operator O14 is also going to have conformal dimension 0. It's basically equal to the identity operator. So there's this identification of operators. It just that the fusion formula does not know about this from the get-go. So the fusion formula, the way that Felinda built it, is like telling you, like, look, you're fusing O12 with itself, then you're ending up with the identity operator and O13, but O13 is O12 itself. So basically, you're fusing it and getting itself back, even though the fusion formula is going to tell you it's O13. Okay. This is just, I think I'm just pointing this out because it gave me a headache some time ago. Very good. As we will see, like, in 1 or 2 slides. Why was this important? And why I was also stressing this fusion formula like this? It's really because we want to understand this, the homogeneous partition function of these minimum models. So, and it turns out that one of the approaches that you can use to calculate this homogeneous partition function is what's going back to, like, the sewing formula. So what this, I think, do you say sewing or swing formula? Swing formula? Okay. The swing formula basically, as it basically says, what it does is takes spheres and sews them together. So there's, for example, for genus 2, you have, like, you use 2 spheres, and then you're basically connecting them with some tubes. So basically, that means that you're inserting some operators here on one sphere, you're inserting the complex conjugate operator on the other sphere, and then you're basically connecting this with tubes. And then you already see that there's a hole and there's a hole, basically. And that basically gives you these 2 holes. So if you want to sew 2 spheres, like 3 punctured spheres with, like, 3 tubes, then you're gonna get, like, this genus 2 surface. And you can just, like, basically can continue along these lines. If you want to sew together 4 spheres with a couple of more tubes, you're gonna get, like, a genus 3 surface. And then just, like, go ahead and, like, get every single higher genus Riemann surface by sewing together spheres. So this is the approach that we use to get the higher genus partition function of this minimal models over here. And why have I been stressing so much on, like, this fusion formula? And because in the end, like, what is important here are the OB coefficients. So because of basically these punctures over here. So then, for example, like in genus 2, which is exactly this example over here, what you're gonna get is that the genus 2 partition function of this minimal model over here, it's basically, so this is a normalization factor over here. So these are basically these 2 spheres. This is the conformal anomaly factor on the 2 sphere, sorry, on the genus 2 surface. And then you basically have, like, the square of these OB coefficients, basically coming from here and here. And this tau over here, they are the moduli. So basically, because you're on a genus 2 surface, you have, like, this this, and this, you basically have these three different moduli. And then, as I was saying, just continue. But in general, for genus H Riemann surface, the genus H Riemann's partition function is going to be proportional to basically this OP coefficients to some power. So the important ingredient in calculating this higher genus partition function are the OP coefficients. And it actually turns out, and I think it's a remarkable piece of work, that Dotsenko and Fateev have been calculating these OP coefficients, I don't know, like 30 years ago. So they have been using the column gas formalism, and they've been calculating, I guess, in a deep, cold winter night somewhere in Russia, like the OP coefficients of this non-unitary minimal models. I think this is beautiful. Like, I mean, I don't think that they had Mathematica and they just got all of this. So I think this is amazing. So exactly. So these OP coefficients, they are known explicitly. And let me just point this out again. We have non-unitary minimal models. The OP coefficients for unitary minimal models, they're positive. We have non-unitary minimal models, so the OP coefficients are no longer necessarily positive. On the contrast, they can be imaginary. So, and for example, like for the Yang-Lee model, so, and here I just wanted to stress this. So the OP coefficients a la Dotsenko and Fateev, I have them here. So I'm gonna explain this like just in a second. The OP coefficients, these coefficients I1, I2, I3, they follow from the fusion formula. That's why I've been stressing this 2, 2, 3 before, like here when I was saying like 2, or 1, or 1, 2, or 1, 2 fuses to 1, 3, because the Dotsenko and Fateev or the OP coefficients follow this rule. So this 2, 2, 3 basically is the OP coefficients of like the 3-point functions of 1, 2 in the Yang-Lee model. And you see it's purely imaginary. If you go to the m = 4 model, which is like the 2, 7 model here, so m = 4 gives you 2, 7, then you're going to find both a purely real and a purely imaginary OP coefficient. So basically, these OP coefficients of these non-unitary minimal models, they can be either purely real or purely imaginary. Now, very good. And I just because for my own curiosity, because I don't know, if I would have seen this talk, I would have been, but show me these OP coefficients now. So I put this one slide here just to show you how remarkably beautiful these OP coefficients are. I mean, this is like basically like, I don't know, it's a two-liner. So, but yeah, these are these OP coefficients. And indeed, like, so these indices, they follow from the fusion formula. Very good. And so basically this, indeed, so what do we want to have? What do we need? We need these OP coefficients. And we need not just the OP coefficients, because the Dotsenko and Fateev already gave us the OP coefficients. We need the semi-classical limit of the OP coefficients. So this is what we've been calculating. So we've been calculating the OP coefficients. And it turns out that if you take operators that are of the form O1 m minus Ri, with the Ri being of order 1. So basically, these are minimal operators. So there's identity operator, and then there are these minimal operators. They have negative conformal dimension. And for these operators, the OP coefficients grows exponentially in M. So these are the OP coefficients for these non-unitary minimal models. They grow exponentially. I think this is also very different than generally, like, I think it's not something that you generally find. So, but indeed, so there's this grow, like this new over here is like, it's of order 1.75. So it's a positive coefficient. So they really grow. So this is basically this behavior over here. So there we are, and then, I mean, there are also other OP coefficients that of course you can study. So you can also study like the minimal light, which basically means that you have two operators of this form O1 m minus Ri, and one operator that is close to the identity operator. But then you already see that, I mean, this operator, this OP coefficients, they are just like growing polynomially. So they can never compete with something that grows exponentially. And then you also have the light OP coefficients, and they're basically just constant. And let me just stress this for a moment. So I don't know, maybe you've been wondering like why there are no light minimal operators. So it just turns out that if you're trying to fuse two light operators, the fusion formula is going to tell you that it can never give you back a minimal operator. So the indices basically are just too far away from each other. So that's really not there because of the fusion formula. So these are the only three possibilities that we can study. But what do we see again here? Like, so basically we realized that there's one dominant OP coefficient. Sorry. There's one dominant OP coefficient. And this dominant OP coefficient is coming from the minimal operators. So if we want to build the genus H partition function, which was the sum of these OP coefficients, the one OP coefficient that was dominating over everything else because it was growing exponentially was this OP coefficients from these things over here. So then basically, that basically dictates us this growth over here. So this is basically this large M, like this semi-classical behavior of the genus H partition function. So it grows exponentially and basically decays polynomially. But I mean, this is really the thing that's driving it, like the dominant piece is this exponential growth. And again, like just the conformal anomaly and the normalization factor. And I mean, here in this N, I'm capturing basically all the moduli dependence. Very good. Okay, so let me just give you the summary again of what we've learned and what we understood. So basically, we've been trying to understand this object over here. This was the gravitational path integral in 2 dimensions, where we have the different topologies that are basically labeled by this chi-h. So I mean, in 2 dimensions, we don't have a Planck scale, basically, a Planck length. So in 2 dimensions, that's basically chi-h. And exactly, so this is basically just giving us the topologies. And then now we've been basically trying to understand this chi-h over here, which was built, or well, which was basically built up like this C Liouville times C matter times C ghost. Very good. I mean, I put the ghost partition function over here. I mean, it's not, I mean, here you can really just follow Polchinski. I think Polchinski gave you all the details for this ghost partition function already. I mean, I'm not stressing too much the ghost partition function too much because it's independent of M in the semi-classical limit. So the ghost partition function is not going to give us an M scaling here to leading order. So it's just a constant basically. But then indeed, like, so we've been trying to understand this, and this for arbitrary genus H on a compact Riemann surface of genus H. And then we understood that if you're on a sphere, so in a sphere, here we get this object over here, where we, of course we had to fix the area, which was unfortunately the thing that we had to do. On a genus 1 Riemann surface, so this is the example that I haven't discussed. This is discussed in very beautiful work of Bershadsky and Klebanov. It turns out that on a genus 0 surface, it basically, you get this logarithm. It's always important, like this scaling of lambda, for example, here. So this is like going as lambda to the power of m, and this is going as lambda to the power of minus m over here. And basically, because on genus 0, you would have basically lambda to the power of 0. So basically, it goes as log lambda. And it goes like linearly in m. And then we saw that on higher genus Riemann surfaces, the OP coefficients were governing our growth. So this is basically where this is coming from. So this comes from the OP coefficients. This piece over here came from Liouville. And this was the normalization condition in the partition function of the minimal models. Very good. So this basically, I think, roughly concludes my discussion of the gravity side. So what we want is that what we have is that we have the semi-classical all genus expansion of the gravitational path integral if you're on a compact Riemann surface. That's in like basically the leading contribution is semi-classical limit. Very good. Okay. Good. So just to summarize again, so basically we've seen this gravitational path integral for a general Riemann surface of genus H. I mentioned what I mean by the semi-classical limit, and we saw the two-sphere partition function, and we also saw the higher genera and the OP coefficients. Very good. Now we are going to discuss this multicritical matrix intervals. I hope I didn't lose everyone, but I hope unless if I already lost you, then maybe at least in the first 5 minutes you understood the bigger picture, and in the last 5 minutes you'll get the bigger picture back. Very good. So why do we? Was this case A? Even though we had to fix the area, which as Panos was mentioning, is tricky. So if you want to fix the area, then this whole interpretation of the sphere partition function gets lost. The problem is just that, I mean, the reason why we didn't pick time-like global theory, where we wouldn't have had to fix the area, was that only in this case A, we had this matrix integral that was conjectured to be dual to this setup. So it turns out that in work of Kazakov, Staudacher, and later Moore, Seiberg, and Staudacher, it was conjectured that this gravitational path integral, like this set graph over here, that was depending on lambda and theta, this two-dimensional gravitational path integral, it has a completion in terms of a random matrix integral. And this random matrix integral is a well-studied object. So this random matrix integral is what's called a multicritical matrix integral. And a multicritical matrix integral is actually nothing scary. On the contrast, a multicritical matrix integral is just a Hermitian matrix integral. So you take a Hermitian matrix, a Hermitian n times n matrix, and pick yourself some m-1 real-valued couplings, and then order this in a polynomial potential over here. And then this thing over here is just a matrix integral. And here, I mean, this is a Hermitian matrix. So basically, we need to, in principle, integrate over all n squared degrees of freedom of this Hermitian matrix. But I mean, this is an object that I mean has been discussed a lot in the literature. So you can basically go to the eigenvalues of this Hermitian matrix M, and then at least for genus 0, you can solve this using even a saddle point approximation. So this is you can just like pick yourself your matrix integral techniques and discuss this matrix integral over here. In particular, like I mean, here we are following like a tuft, like this Fm over here, this log of this matrix integral over here. It has itself a genus expansion. So this is really like what we can compare again with like here, this gravitational path integral, where we also had this genus expansion. So exactly. So we have this genus expansion in the gravity side, we have this genus expansion in the matrix side. And as I was saying, as I was stressing, in this limit where you send this alphas over here to what is known as a multicritical point, while simultaneously taking n to infinity, which is what people call the double scaling limit. In this limit, this thing over here is conjectured to be true. So basically your free energy, this matrix integral over here, corresponds to this, basically this combination of the gravity side over here. And basically, let me already take this ahead because I think it's important to stress this. We are basically, what we're trying to do is that we are trying to relate these two quantities with each other. In the semi-classical limit where this object over here had a sphere saddle. The sphere saddle was tying it again to the Sitter space. Now, why have I been discussing a different genre? I've been discussing a different genre because it cannot just be like, okay, let me fix a single genus because I mean, I like genus 2. So let's work on genus 2. If you're trying to relate these two quantities on a single genus, you cannot really do this because they're going to be normalization conditions. So you cannot really say that, okay, like, I don't know, like F2 is equal to Z2. There are normalization conditions. So you can basically shift theta over here, and then you can absorb everything into theta again. But if you start matching different, like building ratios of different genera, then you can basically absorb all your normalization conditions. So that's why I've been stressing and like calculating the all genus expansion in the gravity side. And I'm going to stress the all genus expansion in the matrix side now as well, because then the punchline is going to be that we are trying to match ratios of different genera so that we can absorb normalization conditions. Because if you decide to fix KH on genus 0, it's not that you can fix it on genus 2 again. You fix it on one genus and then you're done. You cannot fix it again on a different genus. I mean, this is one choice that you can take once in your life, and then nowhere else. Very good. So as I was saying, indeed, so now what I'm going to stress is that I'm going to explain just like in 2 slides, just this genus expansion also of the matrix integral. So we had this Hermitian matrix integral over here, which was built out of these m-1 real-valued couplings. And because you have m-1 real valued couplings, they're basically m-1 distinct non-analyticities. That basically just means that this fh over here is going to go as alpha minus alpha critical to the power of something. So this is what people call a non-analyticity over here. Like this thing over here is fractional. So this is a fraction. So this is a non-analyticity, it's a fractional critical exponent. And because I have m-1 couplings, I'm going to have like m-1 distinct such critical exponents. And let me just remind you again, what have I been starting with in the previously? I started with a minimum model that had itself m-1 Virasoro primaries. So basically there is this duality, so there's this relation between the m-1 primaries of this non-unitary minimum model and the m-1 couplings of the multicritical matrix. So it really just turns out that if you want to turn on one primary of the minimum model that corresponds to a particular tuning of the couplings in the multicritical matrix integral, where you have m-1 distinct organizations of these couplings. Very good. So just to give you some hints of like of what I mean by this distinct non-analyticities. So basically, if you're taking the m=3 example, which was here the matrix potential was just like there was this Gaussian plus alpha 2 over 4 plus alpha 3 over 6. So basically, the m=3 model, which of course from the continuum side, that's the model that was corresponding to turning coupling the Yang-Lee model to gravity. So it's m=3 in the matrix side was corresponding to the Yang-Lee model coupling to gravity. So just like there was this m2 to m-1, that's what we coupled to gravity, which is really exactly the same m as here. So this is what I mean by m here. Very good. And then basically just take either this path or this path. So basically replace this alpha 2 and alpha 3 by this combination over here or this combination over here. And then you're going to find that the free energy on genus 0 is going to scale like in this way or in this way over here, where this epsilon is just a small primary that's very close to 1. So basically, I have a slide on the next slide, on the next page. So in principle, what we're doing here is that we have a path that goes from here to here. So it goes from the origin in coupling space to the multicritical point. This is my path that's parameterized by some time t. So I'm going from t is equal to 0 to 1. So at 1, I'm at my multicritical point. At 0, I'm at the origin. Now I'm adding a small, I'm basically writing t is equal to 1 minus epsilon, where epsilon is very, very small. And then very close to here, very close to the multicritical point, my free energy over here is going to have a specific non-analyticity. And this non-analyticity over here is what we call the non-analyticity arising along the identity path. And this is what we denote the non-analyticity arising along the minimal path, which really comes from the fact that this combination over here is going to corresponds to turning on the identity operator in the minimal model. So as I was stressing here, so I have this non-unitary minimal model, which has m-1 Virasoro primaries, and I have a multicritical matrix integral with m-1 distinct paths to the mth multicritical matrix with m-1 distinct paths. So basically, if I choose to walk along this path over here in the matrix integral, then this path over here is going to correspond to turning on the identity operator in the minimal model. If on the other side, I would have been like, okay, let's do this, I would have turned on a different operator in the minimal model. If I would have done this, I would have turned on yet another operator in the minimal model. So depending on how you choose to walk from the origin to the multicritical point, it corresponds to turning on a different operator in the minimal model. But we want to turn on the identity operator. So that's why we are picking this specific path over here. And in my example here, I was just stressing these two paths, because this is the path that corresponds to turning on the identity operator, and this minimal is the one that corresponds to turning on the minimal operator of this non-unitary minimal model to 2m-1. Very good. And most importantly, like what's really important over here, that for general m, this free energy over here was going as 1 over m to the power of 3. So in the large M limit, we found this semi-classical scaling of the free energy. I mean, I'm just using the semi-classical language here again, because it's again this m going to infinity limit. Very good. And then what you can do is that you can basically just like continue this to all genera. So whereas at genus 0, it's very straightforward because you can just like use a saddle point approximation. If you're trying to go to higher genera, what you're going to use what is known as the string equation. I guess like Felipe and Panos, I guess some of you are very familiar with the string equation. So you're just basically using the string equation, and then you can get all genera. So pick here genus H and calculate the free energy on this genus H along the identity path, which is the path that corresponds to turning on the identity operator in the minimal model. And then what you're going to find in the semi-classical limit, so in this limit where C matter is going to minus infinity, the free energy, for example, on a genus 3 surface, you can just like basically expand it and you're going to find this behavior. And for general genus H, it's going to behave in the following form. So the free energy along the identity path is going to scale as C matter to the power of 3 times H minus 1. And let me just remind you, like C matter was going as M. So basically it goes as M to the power of 3 times H minus 1. So really, if you say H is equal to 0, which was the genus 0 case before, it was as 1 over M to the power of 3. So basically, we also have the all genus expansion in the semi-classical limit of the free energy, of the matrix free energy. And now we're trying to match. Because if we would manage to match this expansion over here, then on the continuum side, we have the sphere saddle and the sublet and basically the connection to the Sitter space. On the other side, we have this matrix integral, which has no length scale. So basically, in principle, it would be the microscopic picture of this gravity side of this Sitter model. And as I was pointing out before, we have this expansion, we have this expansion here. We have basically complete control of this one over here and complete control of this one over here. Actually, let me say it differently again. Like we have complete control of this one over here. The matrix integral is very nice. It really gives you FH for every genus H, and you have an explicit form for arbitrary M. on the gravity side, we have this object over here to leading order. Because if you go to subleading order, you have the moduli dependency, and then it gets more tricky. But we have it to leading order. And then, as I was pointing out, and then of course from what you see over here, so this is the continuum side, this is the gravity side, this is the matrix side. So if you're trying to identify this with this, you have this identification that this theta over here is related to basically like log n over here. So this theta, this coupling of chi-h, is related to the size n of the Hermitian matrix. And epsilon over here, which was this small deformation away from the multicritical point, is related to lambda. And of course, like, I mean, our epsilon was bigger than 0. So that's why we can easily relate it to lambda. And then, as I was pointing out, so we cannot match a single genus. Because if you're trying to match a single genus, you cannot just say, okay, yeah, these two quantities agree with each other in a semi-classical limit. Because if you're trying to do it for a single genus H, you can absorb everything in a rescaling of like this theta over here. But if you decided once to fix the normalization, then you're done. So you can really start to try to match different ratios. So, and here, for example, I mean, I really picked this object over here, and let me just stress this here. So what do we have here? So we have genus 0, we have genus 3, we have genus 2, and we have 3 on top and 3 on the bottom. So there's this overall normalizations are going to drop because how do we organize this expansion? So for genus 0, we have like n squared over here. For genus 3, we have n to the power of minus, I'm getting this wrong, minus 2, right? No, this is 4. Yes, because it's h is equal to 3, so 2 minus 6 is 4. Yes, 2 minus 6 is 4. And then you have n to the power of minus 2 to the power of 3. So these powers of n, if I did this correctly, they should drop out. So this is how you can basically, and of course the same thing happens on this side over here. If you do the analysis in terms of like this e to the power of like 2 theta, e to the power of minus 4 theta squared, e to the power of minus 2 theta cube. So this is the quantity that has all of this gone. So you cannot start rescaling like theta over here anymore because it's gone. It's like canceled out because you took this ratio. This is what you win if you start taking ratios. So you cannot just like match genus 2 with genus 2 or genus 3 with genus 3. You have to start taking ratios. And like, for example, like this thing over here. But this is just an example. I mean, pick your ratio that you want. So, and it turns out that we can actually match these two quantities with each other, at least to leading order. So to leading order, both of these quantities are independent of M, which I think is a really interesting observation. I think it would be incredibly interesting to go to higher, like to subleading order, of course. And this is something that I'm trying to understand right now. Just like at least I'm touching the base of that, the surface of that, because it's very tricky because of the moduli dependency. And very good. So I think this is basically the punchline of where we are at this stage. That the leading order, we could basically match these two different expressions. Well, let me put this importantly, like the one thing that we had to fix was the CFT partition function. So whereas the minimum model partition function for higher genera is very straightforward to calculate, every approach that we tried to calculate the genus 0 partition function of the minimum model failed. So it's remarkable in principle that the genus 0 sphere partition function is not known. So we know what's the conformal anomaly, but the semiclassical approximation of it is not known. So we tried a column Gauss formalism that failed. The possibility right now is to put Landau-Ginzburg on a computer and try to understand Landau-Ginzburg, which is of course a strongly coupled system. So you might not be able to understand Landau-Ginzburg. But I think this, I mean, it was really remarkable that I think the sphere partition function of minimum models is an object that has just been ignored in the literature. I think the reason being is that the sphere partition function on its own doesn't make sense. So, I mean, because why do you want to calculate a sphere partition function? It's a normalization constant, absorb it. If you don't start taking ratios, you don't care about the sphere partition function. In a correlation function, the sphere partition function is modded out. Who cares about the sphere partition function? It's a normalization condition. It's only important if you start taking ratios because then you cannot ignore it anymore. Then you have to keep it. It has to be there. So in 60 years of literature, no one has calculated the sphere partition function of a minimum model as far as I know. Or like I don't know why I picked 60 years, but like in a long standing history, I think the sphere partition function, this poor sphere partition function of minimum models has been ignored. And I think it would be super interesting to understand this in more detail. Very good. But yeah, so let me, hoping that I haven't lost all of you, go back to the bigger picture again. And so our big goal was to understand this Gibbons and Hawking path integral and related to the matrix integral. And because we need to find time models for a quantum de Sitter for de Sitter at the quantum level. And actually, maybe I should have said this also in the beginning. So of course, like what we did is that we are living clearly in a 4D world. It's not that I forgot that, but see, I mean, we go to 2 dimensions because we don't have a microscopic model for de Sitter space in any dimensions. So you have to start somewhere. And so that's, yeah, just to backwards argue again that I didn't lose track of the real world. Okay, good. So all of what's following now is really just like, okay, this is like ideas. These are just like, okay, good. We're just trying to see anything that's hinting towards an entropic picture in this 2-dimensional gravitational path integral. Because in the end, that's what it should be. So somehow this gravitational path integral should encode the de Sitter entropy. So, okay, good. For example, like, okay, as one example, exactly. So we have we are like in genus 0, but this is just, I mean, you can do this on arbitrary genus H. So, but say you're on a genus 0 surface, then you can really like get your you can get the gravitational path integral explicit, the gravitational partition function. You can get it explicitly, And it just takes this form over here. So there's basically this 2 theta over here. And then there's this coefficient of the log. And let me just stress, so this C matter over 6 is not something completely new. So, I mean, like this basically this form, and then maybe I should have written this. Let me actually do this because I think I remember this by heart. So I think it's easier then. Sorry for doing this in real time, but I think it might actually get better if I do this at the fixed area picture. This should be C matter plus C Liouville. I think it should be this. Plus something. Okie dokie. I think if I'm not completely wrong, that it should be this form. So basically, this is just a fixed area picture over here. So I have a leading contribution, which is 2 theta. So, and because you just remember that the theta was basically like log n. So basically, this is log over here. So basically, you have log n over here, log n squared, because of this 2 here. So basically, there's a leading term that goes as n squared. So in principle, like maybe you can interpret this first term as some kind of tree-level de Sitter entropy. Or, sorry, as some tree-level entropy. Let's not even put de Sitter. This just might be a tree-level entropy. And let me stress that this is an n squared, like and the n was the size of the matrix. So this is a discrete number. So an entropy should count something, but better than to take like as an n squared, like it's a discrete number. And then you have the sub-leading pieces over here. And okay, either take this one or take this one over here, but this C matter over 6, like basically if you exponentiate this, then you have lambda to the power of C matter over 6. This is also something that we've seen before. So this is really just like this lambda to the power of C matter of C over 6. This is something that's basically really reminiscent of like the entanglement entropy of a 2-dimensional CFT. And if I would have written this correctly in like, sorry, I have written it correct, but if I would have written it down in terms of the fixed area perspective, then it's basically C matter plus C Liouville minus 26, I think, over 6. So it's basically, you can really like view it as like the entanglement entropy of this combined matter plus Liouville plus ghost sector. And then you have sub-leading contributions over here. And these sub-leading contributions, maybe you can view them as like, okay, this is not a normal CFT, sorry, this is not a rigid CFT anymore, but we're coupling things to gravity. So maybe these are the gravity contributions that are affecting this. So there's no longer just a C over 6, but there are sub-leading corrections stemming from coupling things to gravity. So these are they're arising from the gravity fluctuations. And as I was saying, okay, so there's this entropic hints of this 2 theta over here. But indeed, like these are hints. These are just like, okay, we are just trying to see any hints of like an entropy in the gravitational path integral in 2 dimensions. And now don't panic. So I just put one slide of like the matrix side of an entropic hint. So we're like, I mean, this path integral, sorry, the matrix side is supposed to count to be the microscopic picture of this entropy. It's supposed to capture somehow like the counting problem. But there's one counting problem that's really tied to matrix integrals. So, I mean, a matrix integral has like the Feynman diagrams or this ribbon graphs over here. So one thing that a matrix integral naturally counts are graphs. So there's naturally this counting problem. So, and here, I mean, I'm switching gears. So if you have this picture in mind from before, where I had my surface over here and my multicritical point over here. So here, I'm no longer at the multicritical point, but I'm really close to the origin, of course, because I'm doing a perturbative analysis. So if you're close to the origin, then you have this perturbative expansion where you get this ribbon graph of the matrix integral, which naturally counts something. So for example, there is this number of graphs that have like 9 distinct vertices with 4 to 20 edges. So there's naturally a counting problem in the matrix side. And very good. And then I'm running over time, Felipe. You didn't stop me. I just realized that now. Why didn't you just stop me? Okay, I'm really at the end now. I didn't realize the time. I'm so sorry.
No worries, we're good.
Okay, sorry. if I heard you, I didn't. I'm sorry. Okay, so like, okay, I can also just leave it this way. So this is the outlook. I mean, if I have 2 more minutes, then I can go for my points. But like, please don't let me keep you again.
Use the 2 minutes. You're good.
Okay, good. So that's just my outlook. There are like many open avenues. So I think we opened Pandora's box a bit. I mean, that's at least how I feel. Or let me put it differently. I'm not scared of my postdoc because I know what to do for the next 3 years. So I don't know, whatever you want. So there are multiple avenues that you can explore. So, I mean, as I was stressing, there's this sphere partition function of minimal models, which has been completely ignored in the literature. So I would be super interesting, even if someone of you has an idea of like, because I mean, I think we ran out of ideas at some point, because we tried the column gas formalism upwards and downwards. I think 2 months we were like trying to get it done, but it just, the column gas formalism doesn't seem to be strong enough to get the sphere partition function. The thing is that I'm not a good computer person, so I'm a bit scared of like discussing Landau-Ginzburg and trying to put Landau-Ginzburg on a computer, because I also, yeah, because it's a strongly coupled system, and the potential in the Landau-Ginzburg model for these non-unitary minimal models is either negative or it's imaginary. So either way, it's gonna be a hard problem, and I'm not sure that it leads to something. Very good. Then just going back to here. So basically this over here, we found an avenue to really like test it for arbitrary genus H. So this is the second point over here. So exactly. So the other thing that I think is super interesting, so is maybe, so this is actually something that goes back to Teschner. So we found this very recently, that Teschner has discussed this as well. So that maybe there's even a Sewing formula for Liouville theory. So we use the Sewing formula for the minimal model, but also like Liouville theory is a CFT, the OP coefficients are known as the DOCC coefficients. So can you build a Sewing formula for Liouville theory? I think this would be something super interesting. And I mean, of course, this would then basically give us this functional determinant. So help us understand this functional determinant that we couldn't fix. Then, of course, there's this Lorentzian picture going back to Panos's question. One way of like that we started looking at this is that, so I mean, remember that we had this fixed area condition over here. So we had this S2 b squared x g tilde e to the power of yeah, 2b phi minus 4 pi epsilon. How did I do this? Wait, let me think a second. Yeah, so yeah, so basically you can just like start looking at your yeah, let me see these fluctuations. There should be a fluctuation. Sorry, now I'm getting a bit messed because I'm stressing to finish. So okay, let me maybe discuss this a bit in detail, like if at the end of my talk, and skip it for now. So I mean, one way to look at this Lorentzian picture is that maybe we can absorb some pieces of the fixed area constraint into the cosmological constant, and then the cosmological constant becomes a complex, and then it could be like an averaging problem. I'm happy to discuss this more, just like because I'm running out of time, I'm stressing a bit now. So the other things that are important are non-perturbative effects, of course. So I mean, I've never been discussing, like in all of my talk, I always had n to infinity. So I've never discussed finite n contributions. And now let me say maybe something that's it's a bit tricky, but I mean, the Gibbons and Hawking proposal was basically telling us that we should sum over compact Riemann surfaces. That was the main proposal of Gibbons and Hawking, the compact Riemann surfaces. A matrix integral, however, has non-perturbative effects, and non-perturbative effects are naturally tied to manifolds with boundary. So if the relation between matrix integrals and gravity is actually true, then might we in the end even have to modify the Gibbons and Hawking proposal at least in 2 dimensions? Maybe we have to include manifolds with boundary, even though that was the condition from the get-go not to do. And then the last thing that I just wanted to touch on a second is this time-like Liouville theory. However, the problem with time-like Liouville theory is, of course, that there is no microscopic model known for time-like Liouville theory. So even if in time-like Liouville theory you can basically get a sphere saddle without fixing an area, which avoids clutter and a lot of this annoyance of like Laplace transforming backwards, having no interpretation. There is no microscopic model known, so you're standing there again, like having like no chance to understand the microscopic theory of digital space. But yeah, time will tell. And sorry for going over time. I really didn't realize it, Philip. I'm sorry. Thank you so much for sticking with me for so long, even though I was clearly going over time.
No worries. And, no worries. Let's thank Beatrix. Very nice talk. Do we have any questions from the audience?
I hope I managed to convey like the main message. it's very technical. I completely agree.
Yeah. I think the main message was quite clear. Very nice as well. Good. I think everything was very clear. So thank you, Beatrix, again.
Cheers.
And yeah, let's stop the recording.